Hello, everybody. Welcome to the Global Composite webinar series. And my name is Wenbin Yu, Director of the Composite Design and Manufacturing Hub. This Global Composites Experts webinar series is designed to examine history, present capabilities, and future composites with the goal to sharing the knowledge of composites that has been developed over the past 5 decades. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in the Indiana Manufacturing Institute. All of you are welcome to visit us. We launched the Composite Design and Manufacturing Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. And we envision the CDM Hub to become the premier resource for composite design and manufacturing in the near future. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. You are welcome to join the global composite community with over 12,000 registered users on cdmhub.org. This webinar series is one of the initiatives CDM Hub started as a service to the global composite community. It is made available by the support of CDM Hub sponsors, including Dassault Systems, Tsai Survey, and AnaSwift. We greatly appreciate their financial support for CDM Hub. We invite more organizations to join us to serve the global composite community together. This webinar will be recorded and made available on cdmhub.org. We will email you once the recorded video is available online. The presentation will last about 40 minutes, and we will have about 10 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. For the sake of time, after the presentation, your questions will be summarized and rephrased for the speaker to answer effectively. However, all your questions will be sent verbatim to the speaker for him or her to answer at their discretion. And next, let me ask Professor Dieren Zhang to introduce our distinguished speaker today.
Welcome, everyone. My name is Dieren Zhang. I'm assistant professor of the School of Aeronautics and Astronautics at Purdue University. Today, I'm honored to have the privilege to introduce our webinar speaker, Dr. Steve Tsai. Dr. Tsai got his bachelor and PhD degrees in mechanical engineering from Yale University. He started his work in composite materials at Aeronutronics in Newport Beach, California in 1961. Dr. Tsai was professor at Washington University in 1966 and became chief scientist at Air Force Materials Laboratory in 1968. Later, he joined Stanford University in 1999 as a research professor of aeronautics and astronautics. He is best known for his work in failure criteria, the Tsai-Wu failure criteria, micromechanics, a helping Tsai model, also known as Tsai's modulus, or mini envelopes and the unit circle criteria developed with Dr. Mello, and glueless assembly using native thermal expansion of plus minus 60-degree composite laminates, and his latest mass envelopes that will be the foundation of this presentation. Dr. Tsai has made a significant contribution to our composite community. His latest book on double-double can be downloaded without charge from compositedesign.stanford.edu. Dr. Tsai has been life member of American Society of Mechanical Engineers, International Conference of Composite Materials, and the U.S. Academy of Engineering. Now I will give it to Dr. Steve Tsai.
Should I start?
Yes, yes, please.
Yes. Good morning. This is Steve Tsai speaking to you from Honolulu. We're pleased to have an opportunity to share with you our latest work in composite materials. This work is a collaboration between many of us and myself, people from Brazil to Italy, from Singapore to China, and many other countries. We are trying to share with you what we believe is of interest in the fundamental guidelines for the design and manufacturing of composite materials. There are critiques of composite materials made by the Boeing executives, as we highlighted in this slide. In the first line, that Mr. Burns thought that was not very well understood among the engineers of composite materials. And then Mr. Connors said that if there are innovations, simplicity may be one of the driving forces, rather than making the process more complex. So it is the intent of our work to make composites better understood and to see how simple we can make it rather than how complicated we can make it. We have the keys to our effort to better understand and more simplistic approach. We compare aluminum on the left and the composites on the right. In aluminum, there's a case of isotropy, whereas in composites, we can find the equivalent of isotropy, which we will develop. And very important feature of aluminum and metals is homogeneity. And we too find that if we make composites homogeneous, there are many opportunities that otherwise would not be available. In metals, and including aluminum, constant thickness is the norm. But we think in composites, because of the ability to taper, can save weight and can save significant amount of weight. So we will try to develop all of this. First is the use of trace. Trace is the one master stiffness constant. You only need to have one constant for stiffness. And the value of trace is shown in here. We have 15 different carbon epoxy composites, and these are the value of trace. Trace is the sum of the diagonal terms of the matrix, stiffness matrix. And when you have lamination, and it is important to recognize the separation materials on one side And then you have geometry on the other side. Geometry, in the case of the stiffness of laminate, is a partitioning of the trace. In other words, we have examples of different laminates, 0, 90, and various plus minus 45. It is the same pie, but it's divided differently. And you can see in the 0, 90 is 47%, 47%, and 3%, and so forth and so on. So as you change the materials, you go vertically down. The partitioning doesn't change. Only the size of the pie changes. The size of the pie is determined by the trace. So it is very simple. You only need one constant only that can describe totally all the stiffness of laminates. And this, for example, is a summary of the stiffness. Again, you have the materials on this side, and you have the geometry on this side, and it shows the A11, which is shared by symmetry by A22. You have the A66 here, and you have the A12 here, and then you have the engineering constants. As you can see, that in one sheet, you can capture all the stiffnesses of the laminates. And then in particular, we made a special, this is square symmetric. Square symmetric are these diagonal terms in here. And they are the one that divides. That's the simplest form of laminates, which we will use quite often. And it divides the entire property of the laminates in two parts, what is above that and what's below that. So then we talk about failure criterion. Failure criterion, we will show that the only strength parameter that matter is between x, which is a uniaxial tensile, and x prime, which is a uniaxial compression. And we do this by what we call the omni envelope. In other words, we take the entire lamination, and this shows the strain in the sigma 1 and sigma 2 planes. You can see the angles. These are plotted on the strain basis. And what is left in the middle here, that's a common ground that shares by all laminates. This we call the omni envelope. The omni envelope has one advantage because it is no longer flight angle dependent, so that this is an isotropic space. So this is isotropic space. It makes everything very simple because we can go from strain to principal strain and stress to principal stress. And this on the left is the Tsai criterion. And then we can do the same thing for other failure criteria. What is the isotropic space? And this is a very important simplification, just like that of the trace. And here we can show that we have a typical failure criteria. This will be in we call the first pie failure. Down the bottom is the same laminate, which is the last pie failure. This is an example of IM6 8552, and the lamination happens to be 75 and 15. This is one of the double laminates, and they show that how the radius varies as you go 360 degrees. And so that you can find out what the radius is as a very important measurement of the characteristics of the failure. And that is one parameter. The other parameter is the location of the center as indicated in the cross here. In other words, what determines the failure criterion is the average radius of the failure envelope plus that, and from which we can generate the what we call master failure envelopes, and that will have a comparable simplification implications as we have in trace in the stiffness. So that you can see in this case, we can have the relationship between the average stiffness, and this is for the master ply, for the average stiffness. This is a master ply radius, and this is plotted against the two angles, plus minus phi and plus minus psi. They go from 0 to 90, 0 to 90. And in this particular case, this laminate happens to be 75 and 15, 75 and 15. And this shows how the variation of the radius, and then more importantly, to show that these are really, for all the materials that's available, we have a very simple relationship as a function of square root of x prime. So you have the value of x, the value of x prime. So if you have the new materials not listed in here, you can have the normalized radius as a function of x prime, so you can get an estimate and you can see a fairly good, really, a linear relationship. And the location of the center of the failure envelope has a similar characteristics as the previous ones, and it shows again, this will be a function of square root of x over x prime, and it's fairly linear. And then this is for all the materials, and you will be able to find the two key parameters of failure envelopes, as I said again, is first is the location of the center, and then the dimension, the value of the radius, the average radius of the envelope. So then we can show the transformation. We have a double transformation, and over here is a laminate 30 and 60, and can show of the 15 different carbon epoxy laminates when it is reduced to the radius normalized quantity, and they are almost identical. The only difference is their position, the center location is different. And then you can go from this to this by two transformations. One is you have to rotation about the y-axis, then you have the rotation in plane, and so you can have the mirror image of the two. So therefore, the number of independent failure envelopes are much reduced. And it also on this shows you can interpolate, because the double laminates are field-based. In other words, they have relations between each of the member laminates. Here show the examples of a 75 and 15 and the 60 and 30. In between, you can interpolate, and the result, you can interpolate the result with the quasi-isotropic. And it shows the solid line is the theoretical limit, and the dotted line is the interpolated value. So you can see interpolation is very good, and you can interpolate between different laminates. So we have two examples in here, and here we have a very extreme. You can interpolate between plus or minus 45 and 0.90 in trying to get the quasi-isotropic. And this is quite a distance between the two, but still you can see the difference between the theoretical in purple and the predicted by interpolation is there. So that it is something that is doable. And here are the examples of how you go from the 15 different laminates into the master, and these are the three laminates, and they show the relationship, and they also show the center locations. And so that you can go from individual envelopes to the masters, and then in this way you can go master, you recover the individual. And how well do you do? And you can see again the comparison. And in the first two materials, the conversion is perfect. You can't tell the difference. And in this case, you can see there is a slight difference between the actual starting value versus the one that you recover. And in the middle, it shows a simple, very simple relationship. It has two parameters. R is the radius, and the delta X is the location of the centers. So that you can go from, again, the master here on this side, and you can go back at the arrows as you have seen before. And here are the example of all the failure envelopes. You can see the angles here. For example, you can have a 0 degrees here, and you can have 15, 20, 22 and a half, and 30, and you can have 60 and so forth. And these are the failure envelopes of 3 materials. And these are the 3 materials listed in here. And you can see they are all von Mises-like elliptic envelopes. And the reason they have such a simple relations because they are the isotropic envelopes that we generated, so that no longer they depend on the individual plies. We only deal with the laminate properties, and so that the design process becomes much simpler. Then we talk about homogeneity. Homogeneity is typical of metals and in composites, and it is very important we have homogeneity as well. And this is the double-double. And how we use it, we use R. R is a number of repeats, and then total. In other words, we repeat the basic laminate, say 2, 3, 4, 5, and 6 times. You build a laminate, you build a structure by using the same basic laminate, in which case this is 4 plies now because you have 4 angles, and you repeat it. So this will replace the traditional quad. The traditional quad has many limitations. Among them, it is a discrete combinations. It's not a field-based. So there's a difference between the quad, which is heterogeneous, versus what the double-double is, which is homogeneous. And you can see the quad is very complicated. Among them, the number of this combination, because of the number depending on the basic ply numbers between 4, 5, 6, 10 or more, and into the tens of thousands of combinations in the stacking sequences. Whereas a double-double is much simpler. It only has 2. You only need to have 2 to be able to represent it. So what are the advantages of the double-double? And here are the advantages of the double-double. First, you have a natural symmetry. You have high enough repeats. So how many high is high? You need about 4 repeats in most laminates. So it's 16 plies, and that will become homogenized. And in which case you do not have to worry about mid-plane symmetry. You can have what we call continuous stacking. Continuous stacking is very good because you don't have to keep track where the midplane is. You just go from one end to the other. Then, when it's homogenized, it has no warpage. And you don't have to worry about thermal warpage. And this will be a very, very simple to add hard points. It's very simple to repair because you use basically the same materials. You never have any stress between them. Then, more importantly, the ply drops can be in singles. You no longer have to have ply drops with symmetric placement, so that you have a single. When you have a ply drop in singles, you can place it anywhere you wish. And we recommend that you put the ply drops on the exterior surface. When you do that, and it is very important because you will no longer have any defects in the interior of the laminates, make a much better laminate and much stronger and less likely to delaminate. And finally, you can taper. In lightly loaded area, you can taper. You can remove plies, and then what happens, you can reduce weight and cost. So how much you can reduce in weight, we show you later. You can remove about half of the weight. In other words, the structure you switch to double as compared with a constant thickness laminate. Constant thickness laminate, you can reduce, in many cases, half or even more. Now, in the case of design, and again, it will be much simplification because homogenizations. First, your in-plane stiffness and flexural stiffness are the same, and your coupling matrix is very small, so there's no longer a stacking sequence effect, and there's no issue with blending. So some of the very difficult problems with the design of laminates it has to do with stacking sequence and the blending. And then we can show that you can have a stiffness scaling and you can have a strength scaling. And to make your design, you only need to optimize the structure once, and you can switch materials, you can switch laminates. And then there's show that the interlaminar stress due to a transverse loading is constant independent of lamination. So that will make it very easy because you only need to test one laminate and you only need to be able to generate your allowables. Then in the end, you will have an orthotropic metal and you can have a simple taper that in fact you can do better than metals because you can taper much easier, whereas in metals you cannot taper. And that, of course, you cannot do any of this with a quad because it cannot be homogenized. So how good is double relative to conventional quad? And here's a comparison of the open hole tension, open hole compression, and the CAI. And here are the comparison again. These are generated by different people. And these are generated by Alan Nettles in NASA. And these are generated by people at NIAR. And here are the CAI data. So in all the data we have, there's nothing to show that the double is weaker. If anything, always competitive with the quad, is not better. And in terms of design allowables, and the legacy is to test 4 laminates or 3 laminates, quasi-isotropic, and hard, and the soft. And then there will test a smooth laminate, open hole, and filled hole. And in our judgment, we only need to test one laminate because we only need to know the value of trace and we need to know X prime. And then if we wish to know, we can go open hole tension, open hole compression. And the laminate that we will use, we would recommend the use of 090. The 090 laminate is very easy to do, and it is done today. And one important feature is its low Poisson's ratio. This is the value of the Poisson's ratio, and which means that the laminate is much easier to do, and that the direct measurement A11 and E1 are the same because you have no Poisson's ratios. And therefore, the number of test specimens will go from 18 to 4.5 times, so 22%. And that's all you need. So the barrier presented by the design allowable generation, which is so costly, costly talk about millions of dollars, thousands of specimens, could be much simplified. So then we can talk about rating and scaling. In other words, how do you generate a material? First, we have a concept of strength ratio. Strength ratio is a scalar quantity which is represents the ratio between the applied and the maximum stress. So the way that we apply is a solution of the quadratic equation here in terms of the failure criterion. And the reason this is better is because R equals 1, it represents the failure, while R equals 2, meaning that you can double the thickness or half the double the load or 1/2 the thickness, or if R equals 0.5, that means you can increase the stiffness or reduce the load. And more importantly, which we always use, when the applied stress is unity and the resulting value R is a strength. And there, these are the conditions showing what the various R values could mean. So that we can apply this to 4 loading conditions as an example. The first one is the lower wing, fuselage, upper wing skin, and the wideband. Of the 3 stress components, in other words, you have whatever the value you want, is between 0 and plus or minus 1. So the highest value will be either plus 1 or minus 1. And here is the radius of the failure envelope. And so that you find what is the best laminate. The first one, the lower wing. Lower wing case, the best laminate turned out to be 45 and minus 45. And these are the 15 carbon epoxy materials. These are the working stresses. In other words, what is the stress for each of the 15 materials? Then we do the fuselage. It turns out the best laminate is this. It turns out that the best laminate doesn't change with materials. They are uncoupled. Lamination and the materials are totally uncoupled. Here is the upper wing, and this is the wideband. So that you have these values, then you can we try to rank these materials. We try to rate materials now. Which is the best materials? Well, one way of doing it is to take the average value of the 4 loading cases. Then you divide it, the actual value normalized by the average value, so that you put everything on a common basis. So when you finish, here will be the case of all the materials. And then it turns out you can see the ratings of the materials for the 4 different cases are practically the same. The coefficient of variation are indicated in here. So when you plot it, these are the 15 different materials, and these are the strength rating now. And you can see for each material is subjected to 4 loading conditions. In other words, upper, lower wing, fuselage, and wideband. And you can see that the variation in laminates is insensitive to the materials, so that you have a total uncouple between 2 that you can rate materials. On the left, this rating is by trace. In other words, you want to know how stiff the material is. Here is a value. These are the values in terms of megapascal of the 15 materials, Now you want to know what is the rating of the strength. The rating of strength, well, these are the values. So that not only you know which is the highest turn out to be, 1.78. 1.78 is T800. So that you got total separation, the best material versus the best stiffness. So you can have the highest strength in here, and you can have the highest stiffness in here. So that composite laminate is just like metals. You compare aluminum with titanium, you know the relative stiffness between the two, and you know the relative strength of the two. So you can tell what it is. So it does not matter whether that aluminum is for the upper wing or titanium for the upper wing. And if it's, both are homogenized, both are homogeneous, you know exactly what the ratio is. So we are proposing, knowing this is the same thing for each material. It's just like aluminum and titanium and steel. It has a certain values. So you want to know between one value here, say T800 Cytec versus IM7, and the ratio of stiffness is here, the ratio of strength is here. So that you can have one materials that made with this, and you can scale for the material for the other. So ability to rate, ability to scale is very important because you understand materials better. You optimize for one material, turn out to be, say, 60 and 30, and that will be the same best for all materials. Does not change or change very little. So essentially, this will be the same. Now, this rating system is based on one failure criteria, a criteria we call a unit circle. If you switch to Tsai or other failure criteria, the numerical value change a little bit, but it doesn't change a great deal. The basic concept is the same, and that the material, the rating of materials insensitive to the lamination. So finally, we can talk about the additive manufacturing. Well, here on the top is the conventional practice, and this with the internal discontinuities. So what we recommend, plate drop, there are two options. Either put the plate drop on the outside or put the plate drop on the inside. But within the laminate, you can see there are no disruptions. And this is stiffener made by DFVLR. And then it has a taper, and the taper is the thinnest at the edge, and then the highest in here. And the savings is 41%. And it is stronger because it does not have a peel stress that you have a constant thickness. And here's another tapered beam that is 0 plus or minus 50 and subject to a fatigue test. This was done by Varuna at the NIAR. And to show that with the fatigue, its ability to go 60%. And this has the external plate drops. On one side is on the top, and the other side on the bottom. And these are how much weight savings you have. We have studied this fuselage, stiffened panel, cylinders, and wings. And then there are simplifications of one axis layup. And then you can see 52, 63, 67, and 52. These are percentage of weight savings. This is a fuel tank made by Airbus. And the weight savings are 38 to 48%. This is a study of an adapter by NASA. And the saving on weight is 27%. And here is our approach for a grid stiffened fuselage plug, and that we're able to have a competitive arrangement, but to reduce the production cost. So finally, this is the double-double representations, and that is plus or minus B plus or minus psi. And it has only 4 plies. So when it has 4 plies, particularly you use thin plies, homogenization can be achieved in very minimal way. If you don't like it, you can change to different combinations. But again, the shape changes the penalty you pay is the basic building block goes from 6 plies to 10 plies to 6 plies to 6 plies and so forth. So when the basic building block goes thicker and the number of plies required, homogenization becomes more difficult. So the quad couldn't do it because quad has too many layers. There are 10 layers or 12 layers and so forth. So that it is a heterogeneous. So then we have a book, Double, which you can download. And here's a website. And also we offer free registration or training for graduate students. We waive the registration fee. So in conclusion, we think we can understand composites better, and we can make it more simplistic. And we need to learn how to use trace. We need to know how to simplify and using omni-failure envelope. And then the only two parameters that you really need is x prime. And then we need to do homogenization as a very important feature. And then this is what the double can do. And then you can generate the rating and scaling so that you do not need to recalculations. And you can just scale it. And then finally, a unique feature of composites that's better than metals is the ability to taper. And the tapering will save you weight and save you cost and makes a better specimen. Thank you very much for your attention.
Thank you very much, Dr. Tsai. Here are a few questions from our audience. The first question is, if we design the composite as a quasi-isotropic composite laminate, this will also limit the options for design optional composite parts or limiting some potential capabilities of composite materials?
No, wait a minute. I'm sorry. I didn't understand the question. Could you repeat it again?
Sure. I will rephrase the question. So, do you think when the first topic we talk about the isotropic composite laminate design, will this also limit some of the potential of composite laminates with some special design situations with highly anisotropic behavior?
Yeah, the question is, we use an omni envelope to claim the strength of laminates only limited in the isotropic space. And the question is, how much do we give up? You give up a little, and we can show you how much you give up. And it turns out it really wasn't that much. The penalty was minimal, but what you gain is so much simpler, and you have a much better, this gives you a conservative design. And the penalty is calculated. You can calculate that, but we think that in the end you wind up with a much better and stronger laminate and much simpler laminate that you can scale. You can rate that you couldn't do if you didn't do that. So that what you net gain is greater than otherwise.
Sure. Another question about the trace work you present is there any limitation of this concept? For example, if we apply it to carbon fiber composite versus glass fiber composite, or we have thermoset versus thermoplastic composites, or if there is the accuracy of the model may be affected by the fiber volume fraction. So mainly is what will be the limitations possibly with this trace model?
That's a very good question. Trace works best for carbon epoxy and also the high modulus carbon. Works well with Kevlar, but it does not work well with glass because glass has a lower stiffness, so it's not as shown. But I'd be happy to show you the comparison in terms of glass, and then Carlos Semini and Sung Ha has made a study compared with all the composites. So it works best, and that's a nature of of a trace. Now, in the value trace, the volume fraction is not reflected. In other words, the comparison we show you of the 15 carbon epoxy composites, they have totally different volume fractions. They're all in the 50s and 60s, and it's not sensitive to that at all. So do not take into account. But if your base laminate, suppose your base laminate, reference laminate is 60% volume fraction, and your actual laminate goes up or down, and you can make that correction. You can make that corrections by whatever theory or test data that you have, and to reflect it. And because the value of trace will vary, but the separation, the key is the separation between materials and geometry. So that if you change the volume fraction or you change the condition, use a hot, wet condition or dry, cold conditions, the value of trace changed, but the geometry did not change. In other words, if you have a 090 laminate, the E1 is 47% of trace. That 47% trace doesn't vary, and the 3% is shear modulus, and that doesn't change. And the advantage is you don't really need to measure shear modulus. It is 3% of trace. If you know the value of trace, your 3% is your shear modulus, and that is better than you can measure because shear modulus is so difficult. It has a nonlinearity, and then the test method is really very complicated. So you can make much simpler conditions. As we said, you only need to test 090 laminate, and you measure E1. You say what is value of trace? Value of trace is 88%, or if you use a 090, is 47% of trace is E1. So that you measure the E1 of a 090 divided by 0.47. That is your value of trace. And from that value, you can get the stiffness of all laminates made from that material. So it is that simple.
Thank you so much, Dr. Tsai. There are also a couple of questions about how your work compares with classical laminate plate theory. If you would like to comment some of the main limitations of the classical laminate plate theory, that you think will be like how the work you develop is actually more advanced and better than the classical laminate plate theory.
The principal difference between what the double-double and the classical laminate, which we call a quad, is that the double-double is field-based. In other words, all the members of a laminate, of course, depending on the angle increments, we show 15 degrees. In other words, the increments are 15 degrees. Say you can have 0, 15, 30, 45, 60, 75, and 90. So you can have higher increments or lower increments, whatever you wish. But the key is that all the members of the families are evenly distributed, and they are connected by transformation properties. As we showed, you can interpolate, you can do extrapolate, and so forth. And it is very easy. You have a better coverage for what is available. Now, quad, on the other hand, you start out with a 090 plus or minus 45. You start with 4 plies. You want more directional properties. You have to add plies. So you go from 4 to 5 to 6 to 7 to 8. In other words, you want to have 3 zeros, 2 90s, or whatever you want. So whatever you do, you add plies. You go from 4, which you cannot use because you have to go to 8 because you need a symmetry. And therefore, you suddenly have the basic block is 8. Then ordinarily you have a 10-ply sublaminate, and then the basic laminate become 20 plies. And you cannot get anything homogenized. These are discrete values. In other words, you have no connection between them. You cannot interpolate. You cannot interpolate two laminates. And so that you have very uneven distribution because you have 6, 8, 9, 10, and 12. So it's totally different. And then the most important part, the inability to homogenize, then to capture what you may do with a double-double, which is a much simpler laminate. And then the homogenization, as we say, because it's naturally symmetric, it is easy to do. And above all, you can reduce the thickness. You can reduce the thickness by reducing the number of repeats. In other words, if you have 10 repeats, so you have 40 ply laminates, you can go from 10 to 9 to 8 to 5 and so forth. As you reduce the number of repeats, the property of the laminate remain the same. You do not change the laminate. Whereas if you use a quad, you want to change the laminate, you drop plies. Well, if you have 5 zeros in the laminate, you go to 4 zeros, well, the laminate is no longer the same. And so your optimization becomes so difficult. And you have a problem in the stacking sequence. You have thousands and thousands of stacking sequences. So for each one you do is totally different from the next one. And it was interesting. I asked Airbus, one of the wing designers, say, how much weight did you save as compared with aluminum? They say they do not know. I say, why do you know? Why do you not know? He said, well, because they did not calculate for the aluminum. The reason is that they had such a heterogeneous design, there's no way to compare. Whereas if you have a homogeneous structure, then the rating system tells you exactly how much you will be as compared with aluminum. As you can switch materials, you can switch laminates, and that allows you to scale. So you only need to design once. Another example, like the fan blades that General Electric provides. For each engine, they have design for the blades. They cannot scale, and every time they design, they have to start from scratch. And so the reason is they do not do a homogenized laminate, and therefore there's no way they can scale. And so there's a lot that you can learn, and that we think is that will make composites better understood and much simpler and much easier to do.
Thank you so much. There's also a question about can the work you present today also apply to textile composites like woven fabric composite laminates in terms of the trays and the strength anatomy, the models?
Well, in terms of fabric, trace works exactly the same way. In other words, you treat the fabric as if it's homogenized. We use non-crimp fabric, for example, and we just treat that as a laminate. And so fabric, you have different weaves. So it depends on the degree of modeling that you wish to do. In the case of fabric, we would treat a fabric as one homogenized layers, and then you can apply the same for the stiffness and same for the strength. So that should work. In fact, we can show you the data that we have, and it turns out that for square fabric, and it works very well. That 47%. For that, it works. The modeling of the fabric, square fabric, as a 0.90 works very well.
Thank you very much. So another question for the double laminates is, would you like to comment on the manufacturing effect? Does it showing also better manufacturing tolerance control for the double as compared with quad?
The control of double, depending on your process, that can vary from hand layout to fiber placement and tape laying machines and so forth. There's no difference. In other words, you can, in the automated layup sequence, you can do plus or minus 28 as easily you can do any other angles. And you can do the ply drops. So when you do a homogenized laminate, it is just as easy. In fact, it's faster. You're less likely to make mistakes. And when you have the ply drop on the exterior surface, it gives you a much better way for inspection to make sure you do not make a mistake. You see each ply. Whereas you have ply drop in the interior, now you do not see that anymore, and that you have no idea what they are. So the use of double with the automated tape laying machine is the same, and so it does not add any more value to it. In fact, it's as simple as that, and we don't see any penalty.
Thank you. Then for the double laminates, does that mean we can do? Is there any concern with the delamination initiation if we place the ply drops at the exterior side only?
That's a good question. In other words, if the ply drop is on the exterior surface, do we have any problem in terms of separation? The peel? The fatigue test, for example, that Waruna did at NIAR, we did not have any peeling or debound. We did not have a cover. We did not have a additional layer of fabric on the outside, and so we did not show any difficulty. And so far, we do not see any problem. But again, the number of test data that we have is still limited. But conceptually, it is so much better to keep the inside, the interior laminate free of discontinuity. It makes the processing easier if you do the liquid molding infiltration process. And then above all, intuitively, you would expect a much higher resistance to delamination. And there are many advantages that you wouldn't have otherwise.
Thank you. Probably our last question is there any commercial available FEA software that implement your stiffness strength calculation methods so that we can use it for our composite design? Yes.
Yes, one of the best software that we have is we call LAM Search. So the rating system to find the best laminate, we have a Excel-based called LAM Search. This is like a search engine in a simpler version of it, of Google for laminates, and that we have. And then those who want to have it, you can contact us. We send it to you free, and it's very easy to do. It needs a little training. But basically it's Excel based, so you see the total thing. You can have multiple load conditions like what we did. We showed the fuselage, upper skin, lower skin, and other cases, and then it can give you different angle increments, 15 degrees or 7.5 degrees, and so forth. Give you what is the best laminate. And we have 4 failure criteria, the unit circle, which we have used, and also Tsai and max strain, and then so forth. So it's very easy software. And again, we offer free for graduate students to participate in our workshop. The next one is January 22nd next year.
Thank you very much, Dr. Tsai, and thank you very much for everyone participating in this webinar. More questions will be answered on our cdmhub.org, and our upcoming webinar will be February 2nd, 2023, by Professor Tucker on the topic of fiber orientation prediction for discontinuous fiber composites. We look forward to seeing you in New Year and have a wonderful holiday season. Bye-bye.